Welcome, everyone. Let's get started. We'll come back to this problem in a few slides. Course announcements. There will be office hours today, as usual, right after class. And here's a puppy. Are there any questions? So I promised graph algorithms today. I'm sorry, it's going to be a couple more classes before we get to graph algorithms. Today is actually going to be about asymptotic notation and sorting, but we are getting there. I just realized that we should probably do a couple of other things first, so I reshuffled. Okay, let's get started. So asymptotic notation. This is often called big O notation. And there are a few different notations wrapped up here. The first one is literally called big O. So we write f of x is big O of g of x if there is some constant, a positive constant, and some value x0 such that f of x is less than or equal to c g of x whenever x is bigger than x0. So basically just like decoding that a little bit, that there is some multiple of g of x so that f of x is at most that multiple of g of x for x big enough. So g of x dominates f of x when x gets big. For example, if you had f of x equal to 2x squared plus 1 and g of x equal to x squared, then you could write f of x is big O of g of x. 2x squared plus 1 is big O of x squared. And for example, one of the ways you could pick c there are many different ways. You could pick c, for example, to be 3 because this is true for x sufficiently large. Notice that you could also write 2x squared plus 1 is big O of x cubed, because it only goes one way. It's just saying that it's less than or equal to a multiple of, or less than or equal to a multiple of g of x for x sufficiently large. Are there questions about this? Some people will write this as set notation. So f of x is in big O of g of x, but we're going to use equal. What could we write? What could we write, for example, for x cubed plus 100 x squared? What would be some examples of, if that were our f, what could be our g? For example, x cubed, or x to the fourth, or x to the 100, or e to the x, or many other things. Yeah. And for example, if it were x cubed, you could just choose c to be 2, because 2x cubed is greater than or equal to x cubed plus 100x squared. Okay, little o now. So little o means that for every constant c greater than 0, there is some value x0 such that f of x is less than c times g of x for x bigger than x0. So if x is large enough, then f of x is, so for any multiple of g of x, f of x is eventually less than that multiple. For example, if f of x is x squared and g of x is x cubed, then we have x squared is little o of x cubed, because if you pick any c greater than 0, the statement x squared is less than cx cubed holds when x is sufficiently large. This wouldn't hold if you wanted to make it be x squared here. So x squared is little o of x cubed, but it's not little o of x squared. It is big O of x squared, but it's not little o of x squared. Other questions? what could we write for x log x? If that were our f of x, what could g of x be? Well, it's x log x is little o of some things. What could those things be? More suggestions. So there are several options. We could, for example, say x log x is little o of x squared. We could also write little o of x squared log x. Anything that is asymptotically strictly bigger than x log x. So think of big O as asymptotically greater than or equal to, and little o as asymptotically, sorry, big O as asymptotically less than or equal to, and big O as asymptotically strictly less than. So why is this true? Well, in order to prove this, we would need to show that for every c greater than 0, we have x log x is less than cx squared for x sufficiently large. In particular, if we make c be very small, but still bigger than 0. Now, we can rearrange this to be just 1 over c log x is less than x. This is an equivalent statement. And this is an equivalent statement. X to the 1 over c is less than e to the x. And this is true for x large enough. 1 over c might be some very large number. For example, c is 1 over 1,000. You have x to the 1,000, but that is less than e to the x for x sufficiently large. And I'm not going to prove that, but you can show that. Are there any questions? Okay. People abuse this notation all the time in analysis of algorithms. There are so many ways that this is messed up. I mean, you can see that I've heard it said that something is at least O of x, which actually means absolutely nothing at all, because being O of x of something means you are less than or equal to something. So there are three more notations here. I'm sorry for going through all of them. So this big omega, this is backslash omega with a capital O in LaTeX, if you're curious. And the other one here is backslash omega with a little o. It's just a capital and lowercase versions of the Greek letter omega. And so this is true if f of x is big omega of g of x, if g of x is big O of f of x. That is, if there's a constant, a positive constant c and a value x0 such that f of x is greater than or equal to c g of x whenever x is greater than x0. So this is saying that, so remember, big O is like asymptotically less than or equal to. Big omega is asymptotically greater than or equal to. So for example, if you had f of x equals 2x squared plus 1 and g of x is x squared, we have 2x squared plus 1 is big omega of x squared. We also had that it was big O of x squared. But it's even easier to prove that it's big omega because you can just take c equals to 1. We can also write little omega, and little omega is, again, it's like the opposite of little o. Just like big omega was the opposite of big O. And so we write f of x is little omega of g of x if g of x is little o of f of x. That is, if for every constant c greater than 0, there's a value x0 such that f of x is greater than c g of x whenever x is greater than x0. So this is the asymptotically greater than, strictly greater than. So for example, x squared log x is asymptotically greater than little omega of x squared. Are there any questions here? Okay, and finally we have theta. We write f of x is theta of g of x if both f of x is big O of g of x, sorry, there should be a closed paren there, and f of x is big omega of g of x. So it's asymptotically greater than or equal to and less than or equal to g of x. And this is written backslash theta with a capital T in LaTeX. For example, since we saw before that 2x squared plus 1 is both big O of x squared and big omega of x squared, we have that 2x squared plus 1 is big theta of x squared, just theta of x squared. What about if f of x is little o of g of x and little omega of g of x? What's the notation for that? Ah, yes, it's not possible. That would mean that something is, f is asymptotically strictly less than g and strictly greater than g. So it's not, it's just a trick question. There is no notation for that because it's not possible. Okay. Some examples. This is a sequence where just anything later in the sequence is asymptotically bigger than anything earlier. So like x to the fourth is asymptotically bigger than x to the third, x squared, x log x log x. Why is x plus 1 to the 10 big theta of x to the 10? Just as an example. Yeah, these are all good suggestions. We can just expand it out with a binomial theorem, and we get this polynomial of degree 10, and any polynomial of degree 10 is going to be big theta of x to the 10. In this particular case, we could just say 2x to the 10 is going to be eventually bigger than this, because x to the 10 is going to dominate all of these other terms for x sufficiently large. So that means that x plus 1 to the 10 is big O of x to the 10. It is asymptotically less than or equal to x to the 10, but it's clearly asymptotically greater than or equal to x to the 10 because it is literally greater than x to the 10 as well. So yeah, if x is very large, it's between x to the 10 and 2x to the 10. It's also between x to the 10 and like 3x to the 10 or 10x to the 10 or 1.5 or 1.0001 x to the 10 will also be asymptotically bigger than x plus 1 to the 10. This has to be any number bigger than 1 for this to be true. Good question. Any more questions? Okay. Simple operations. If you have f of x equals big O of g of x, then c times f of x is big O of g of x for any positive constant. And if you have two things that are both big O of h of x, then their sum is also big O of h of x. The same thing holds true for any of these other notations. Okay, so why is this useful? We will often use, can you hear me okay? We'll often use asymptotic notation for assessing the time or the space required for an algorithm as a function, say, of input size. And that's because the constants are often less important than how the time scales with the input. For example, theta of n squared is generally going to be much worse than theta of n for reasonably large input. That may not always be true. Sometimes the constants involved in here will actually be, sometimes asymptotically it will be better or it'll be worse, but for small n, the constant on this is going to be much bigger sometimes. Generally, this is much worse. Also, the constants will often depend on the units we're using or the particular hardware. So doing some kind of mathematical analysis it's easier to drop the constants. Okay. So now let's look at just what is the time complexity of an algorithm. This is a way to quantify how much time it takes to run the algorithm. And it's possible to think about worst case time, so the maximum amount of time it takes to run, or about average case time. You could also, and that's the average amount of time it takes to run over all possible inputs. You could also think about the best case time, but that's not thought about as much. So today we will be thinking about sorting. The problem is, given a list of n numbers, all of them different, put them into increasing order. We don't know what the n numbers are. We just know that they are different. We want to order them. We will look at a few different ways to do this. Oh, question about the previous slide. Is it true that max time is approximately average time, right? No, max time is worst case time, and often worst case time will be significantly worse than average time. It is always going to be greater than or equal to the average time. If you think about it, the max of something is always greater than or equal to the average, and the min is always less than or equal to the average. But we will see situations today where the worst case time is actually different from the average case time. Sometimes it is the same, sometimes it is not. Very good question. There's also a notion of amortized time complexity. And yes, we will be getting to amortized complexity later, but not today. Okay. So let's do the first cut at how to do this. Insertion sort. This is probably what you're doing if you're like sorting a deck of cards, or at least I do this if I'm sorting a deck of cards. I'm not like employing heap sort or something. So the way this works is you're sort of creating a new list one number at a time. For every number in L, you're just going through the numbers in L. You're working out where it should be, and you're progressively making this list L prime longer, and you're adding it there. So for example, starting out with L being this, I'm just going to add now, like I take 5, I'm going to put that down. Now I'm going to take 2, and I put it before the 5. Take 6, and I put it after the 5. Put 1, and I put it before the 2, and so on. Okay. So let's analyze this. Let's work out how long it takes. Suppose we're taking the kth element of L. We've done k-1. We're now taking the kth element, and we're inserting it into L prime. So to insert it into L prime, or at least naively doing this, we can first move it to the end of L prime, and then iteratively swap any elements of L prime lower than it. So first, I'm inserting this 3, and I'm going to be like, oh, well, these things are already sorted, so I'm gonna put it at the end. Does it work at the end? I compare it to the last element. Nope. Swap the 2. Compare this to the 5. Need to swap it again. Need to swap it one more time. And now if I compare it to the 2, I'm done. And it's pretty clear that this will work. So this is going to take mk steps, where mk is the number of spots from the end of L prime that we have to move. Okay. So here I had to move like 3 or 4 steps, depending on how you count it. Okay. So the overall time of the whole algorithm is then going to be just the sum of all of these mk. I do this with the first element of L, and that's really easy. L prime is just a single thing. It's just that one thing. And then I do the second element of L, and I have to work out whether to put it before or after the element that's already there, and so on. What is the worst case time complexity of the algorithm? Yeah, the input would be worst if we had things in reverse order. And in the worst case, we have to move this thing all of the spots that it could possibly move. And that happens exactly when things are in reverse order. So the thing that we're adding is before all of the things we've already added. So that means that we started out, L had everything in decreasing order, and then we're trying to turn it into increasing order. If we knew that from the start, then it would be really easy. But if we don't know that, if we're just doing insertion and sort blindly, then it will end up with mk equal to k for every k. And so that means that m is just the sum from k equals 1 to n of k. And we know that that is n times n plus 1 over 2. And that is big theta of n squared. Okay. So worst case here is big theta of n squared. Or theta of n squared, sorry. Questions? Okay. What is the average case time complexity of the algorithm? And why? Okay. Yeah. So we're looking for the expected value of m. And we know that m is equal to the sum of mk, the amount that we move at each time. We move the kth thing. What can we use? Linearity of expectation, yay. Okay, so the expected value of m is just the sum of the expected values of mk. What is the expected value of mk? Remember, mk is how many steps we have to move the kth thing when we're inserting it into L prime. Yeah, so since the first k elements of L could have been in any order, mk is equally likely to be any one of the possibilities, 1, 2, 3, all the way up to k.
So that means that the expected value of mk is just the midpoint of all of those, which is k over 2. And so now we have that the expected value of m is equal to the sum of all of these expected values of mk, which are just k over 2. So we have the same thing that we had before, only divided by 2. It's n times n plus 1 over 4 instead of n times n plus 1 over 2, because it's k over 2 instead of k. But that's still theta of n squared. So in this case, the average case complexity is the same asymptotically as the worst case complexity, but it is still going to be faster. It's just only by a constant. Are there questions? N squared is the same complexity as n squared over 2 in these terms. Yeah, because we're neglecting all the constants. So just by writing theta of n squared, that means that a constant times n squared. It is asymptotically equal to a constant times n squared. Faster by constant could definitely be useful. In this case, insertion sort kind of sucks from a scalability perspective because we're going to get better than just a constant. But yes, faster by constant is not to be sneezed at. Okay. Could I walk through exactly why this ends up being big omega? Yeah, exactly. Oh, sorry, why it ends up being big omega rather, yes. So this is theta of n squared, which means that it is both big O of n squared and big omega of n squared. So big O of n squared means that it is asymptotically less than or equal to n squared. And it is the case that n times n plus 1 over 4 is asymptotically less than or equal to n squared, because it is literally less than or equal to n squared. So it is the big O direction is clear. Now, why is it greater than, asymptotically greater than or equal to n squared? Well, it's asymptotically greater than or equal to n squared because we can just multiply n squared by a constant. Remember that the way that big omega worked is that we could say that f of x is big omega of g of x if there is some constant c such that for x sufficiently large, f of x is greater than or equal to c times g of x. And in this case, if you take, for example, c equals 1/4, that would work. Good question. Let's move on. So we can also use a dynamic programming paradigm, dividing the problem into multiple smaller problems and solving them separately. For sorting, this is going to give us the merge sort algorithm. Also the next one that we're going to look at, which is quicksort. So we're going to divide the full list into lists L1 and L2. We're going to sort each of L1 and L2 recursively with the same algorithm. And then we're going to merge the sorted lists, keeping them sorted so that we end up with something that is in the end sorted. So for example, if we were trying to sort this, we could merge what would happen is, if I'm going to assume that we've divided roughly equally into L1 and L2. So we divide into 526 and 143. We sort each of those individually, and then we merge the results. But we have to do this recursively, right? So how do we get our sorted 526? Well, we merge the sort of 5, 2, and 6. And then for this, we merge the sort of 1, 4, and 3. So 5, 2 sorted is 2, 5. So bring this back, we have merge of 2, 5, and 6, and then merge of here 1, 4, and 3. So we have 2, 5, 6, and 1, 3, 4, and we're merging those, and then we end up with 1, 2, 3, 4, 5, 6. Now, it remains to be seen exactly how we're doing this merging, because it's not, I haven't said how we merge 2, 5, 6, and 1, 3, 4. So let's talk about that now. How do we do the merging? Well, suppose we have two sorted decks of cards. I really like these decks of cards, I guess. We could flip the top two cards, so the min of each deck. And we can take the min of those two, and that's our min overall. It's definitely the min of one of those lists. Then we flip the card below it, the one that was below what we took off. And then we take the min from those two. And that has to be the min of the resulting list. We keep on doing this. Each time we take the min of whatever sort of the two candidates for the min are, the min in one list and the min in the other list, and we add that to our new list. So for example, if we're going here, we say 1 and 2, which is smaller, 1. 1 goes here. Now we have 2 and 3, which is smaller, 2. 2 goes here. Now we have 5 and 3, which is smaller, 3 goes here. 4 and 5, 4 goes here. Then we're done with this list, and so we just put the rest of this list in here, 1, 2, 3, 4, 5, 6. If the lengths of L1 and L2 are N1 and N2, how long does this take? Worst case. Is it the max? I think of it as the sum, because you could end up having to flip all of the cards, basically. You could end up alternating between the two. And you're having to, each time you flip a card, you're going to have to compare it to the other candidate. So you're basically, you could end up having N1 plus N2 comparisons. And then I've added a constant here because we don't know how long it takes based upon your algorithm to do the comparison. So constant time for each one of the comparisons, but you might have N1 plus N2 comparisons. OK. So what's the worst case time complexity for the whole algorithm? OK. Let's set f of n to be the worst case time for a list of length L. Sorry, n. A list L of length n. So we need to sort L1 and L2 and merge them. So if n is even, that will give us f of n is f of n over 2, that's L1, plus f of n over 2, that's L2, plus the time it takes to merge them, which we said is c times n2 plus n2. This is just 2f of n over 2 plus cn. OK. Now, let's just assume that n is equal to 2 to the k. It's going to be a bit easier to do this analysis. Let's just go through this. Now, this is really an induction proof in disguise, but the way that I would see it is I would think of doing it sort of one step at a time. I would say like, so this first line is just literally what this is, just substituting in 2 to the k. So here you have f of 2 to the k is equal to 2 times f of 2 to the k minus 1 plus 2 to the k times c. So literally substituting in 2 to the k for n. So this, we could apply the same, this is a formula that we can apply to f of 2 to the k minus 1 itself, recursively. So we apply it in here, and we get the same thing as this, only inside and with k minus 1 instead of k, and k minus 2 instead of k minus 1. Now let's expand that out, and we get 4 times f of 2 to the k minus 2, plus, and then the 2 and the 2 to the k minus 1 become another 2 to the k, and we have 2 times 2 to the k c. I have a 2 to the k c here, and a 2 to the k c here. Now we can apply our formula recursively again to f of 2 to the k minus 2. And here we get 2 times f of 2 to the k minus 3 here, plus now 2 to the k minus 2c. And then again, we have this term, which is still just outside hanging out. And now we multiply by 4, and we get another 2 to the kc here. So that becomes 3 times 2 to the kc here. And here we have 8 times f of 2 to the k minus 3. There's a question. Why are we substituting n equals 2 to the k? That's just so we don't have to worry about ever ending up with an odd number. It just means if we didn't do 2 to the k, we'd have to just use the floor function, where floor of n is just the greatest integer less than or equal to n. And that's totally fine. Exactly the same analysis will hold. This is just to make all of these things nice integers. OK, so here we have 8 times f of 2 to the k minus 3 plus 3 times 2 to the k c. And we can see the pattern, and we can easily prove the pattern, for example, by induction, that we're going to end up with 2 to the k times f of 1, and all the powers of 2 are coming out. And this k comes out here. First we had 1, 2, 3, and we'll eventually have k times 2 to the k c. And f of 1, well, f of 1, you've already sorted that list. So what we actually have is k times 2 to the k c, because f of 1, it's done, 0. So this is theta of k times 2 to the k, because it's just literally a constant times k to k times 2 to the k. So you just pull out the constant. And k is equal to log n, or log base 2 of n. And n is equal to 2 to the k. And so up to a constant is n times log n. So it's theta of n log n. Again, this is asymptotically equal to n log n. It's not asymptotically greater than or asymptotically less than. You could also write that it's big O of n log n, but that wouldn't be telling you as much. Questions? Was it induction because we looked at k, k minus 1, k minus 2, etc.? Yeah, well, there was a step here where we basically used induction. So this, if you really want to be super formal about it, you could, when you went from to here, you could prove it by induction. And it will be a really fast proof by induction. The reason why I didn't just prove it by induction from the start is because you would have to know what the formula is to start out with the induction. Typically, an induction proof is really easy if you know what the formula is that you're trying to prove by induction. Here I was trying to show how you would get to that formula if you didn't already know it. Good question. Yes, a quick question of f of 1 being 0. Yes, it's f of 1 is 0 because this list is already sorted. If you want, you could make f of 1 be like 1 or a constant or something, and it's not going to change anything because 2 to the k is less than k times 2 to the k. It would just change this constant c. It's not really a problem. We don't have to worry about that. So it's a similar analysis. If n is not exactly a power of 2, it'll just be the same thing. It's just, again, we have to work with floor functions. So we have f of n is equal to theta of n log n. So we can also show that the average case time is theta of n log n. I'm not going to go through and prove that. But in this case, both of them are n log n. Previously, both of them were n squared, so we're getting better. N log n is better than n squared. And merge sort is indeed better than insertion sort. The constants are also better. OK, so this will be useful now in the next thing we prove. Prove that for integers, n at least 2, we have that log n is between 1/2 plus 1/3 plus 1/4 all the way up to an nth, and 1 plus 1/2 plus 1/3 plus 1/4 all the way up to an n minus first. How can we do this? We could take the exponential of both sides. I'm not sure if we can use Jensen. We might be able to use Jensen. There's actually a simpler way. But yes, we could have taken the exponential and used this definition of E, remember, as like a limit of stuff. But there isn't a need to. So what's the area under the curve of this particular curve? It's not immediately clear why this is related, but what's the area under the curve of y equals 1 over x between x equals 1 and x equals n? It's just going to be equal to the integral from 1 to n of 1 over x dx. And since the derivative of log is 1 over x, we have log n minus log 1. And log 1 is just 0, so it's equal to log n. Here's where the magic happens. Let's plot this on a graph here, or 2 graphs. Here's this function. We can upper and lower bound the area from 1 to n. Let's suppose n is like 6. Well, the area under the curve from 1 to 6 is included in the area of all these boxes. Box of height 1, box of height 1/2, box of height 1/3, 4th, 5th, and so on. So the area log n is upper bounded by 1 plus 1/2 all the way up to 1 over n minus 1. In this case, n is 6. But we could also do a lower bound here. What's the area under the curve? Sorry, I mean, what is a lower bound on the area under the curve from 1 to 6? We can have these boxes under the curve. This one is height 1/2, because this endpoint is on the curve. This one is height 1/3, 4th, 5th, and 6th. So the sum from 1/2 up through 1/6 is a lower bound to the area log 6. So we have that log n is lower bounded by 1/2 plus 1/3 all the way up to 1 over n, and upper bounded by 1 plus 1/2 all the way up to 1 over n minus 1. So asymptotically, this sum is equal to log n. If you want that this sum is theta of log n. Questions? You can think about what that means for the problem you just proved on the PSAT. It's not gonna tell you how to solve the problem, but it will tell you what the asymptotic formula is. There's a reason why people think of coupon collector as having a nice asymptotic formula. Okay. So now, with that in hand, let's look at Quicksort. So Quicksort is another dynamic programming approach. The way it works to sort a list is to take an element from somewhere in the list, X. This is called your pivot. You go through L one by one, and you pivot using X. You put anything in anything in L that's lower than X in L1, and anything higher than X in L2. You can compare everything in L and divide it into 2 based upon this pivot. And then you're going to sort L1 and L2 using your sorting algorithm. So you apply Quicksort recursively to L1 and L2. And then you're going to combine them in that order, L1, X, L2. You don't need to do any more sorting because you know that everything's already sorted. Okay. So as an example of pivoting around 4, you take out 4, and you say, OK, well, the things that are less than 4 are 2, 1, and 3 in that order, and the things that are greater than 4 are 5 and 6 in that order. And you just sort 2, 1, 3, and you just sort 5, 6, and you put them together, and that is your final output. You need to apply it recursively to 2, 1, 3, and 5, 6. There are many ways to choose the pivot. You might have chosen the pivot to be 6. You might have chosen it to be 1 or 4 or 3. Let's assume it's random. The way you pick the pivot is random. Are there any questions about this? How long does each pivot take? Like dividing it into the less thans and the greater thans. Length of the list. You have that number of comparisons. We have to compare X to every element of the list, so C times N time. So if you have the total time to sort a list L is f of L, then we have f of L is f of L1, because we have to sort L1, we have to sort L2, and then there's that time to do the pivot, which is Cn. Again, N is the length of L. What is the best pivot that we could pick? We're doing it randomly, but suppose that somebody gave us, suppose that the randomness was in our favor. Like, what would be the nicest pivot we would be happy about? Yeah, the one right in the middle. Best pivot is intuitively the midway point of the list, like that half of the things are above it and half of the things are below it. Remember, we don't know what the midway point of the list is, right? So it is, and the list, we don't know even what the numbers in the list are. So we don't necessarily know how to pick the midway point. But if we could pick the midway point, then that will be what we would want intuitively. If that happened, what we would have is we would have f of n equal to f of n over 2, because that's the length of L1, plus f of n over 2, plus Cn. And we saw, in the case of merge sort, that means that f of n is going to be theta of n log n. So if we could somehow pick the midway point of the list always, then we would have theta n log n time. But we don't know what the elements of the list are, and we don't know what the midpoint is. And we could compute the midpoint, but that's going to take a bunch of time. What's the worst pivot that we could pick? the worst pivot, intuitively, is the one that does the worst job of dividing the list into two. So the greatest or the smallest element. I'm not going to prove this, but it's straightforward to prove. It's pretty intuitive. Sort of the opposite extreme to exactly dividing the list. And so what we have here is we have now f of n is f of n minus 1, the length of L1, or potentially the length of L2, plus f of 1, which is the length of the other list, plus Cn, the time it takes to compare everything. And so what we have, is f of 1 is, again, 0. So f of n minus 1 plus Cn. But we can keep on applying this recursively. It's equal to Cn plus C times n minus 1 plus C times n minus 2, and so on all the way down to C. So that's equal to, if you just pull out the C, it's C times n plus n minus 1 all the way down to 1. And so that's C times n, sorry, this should be n plus 1 over 2. And that's theta of n squared. So in the best possible case, we have theta of n log n. In the worst possible case, we have theta of n squared. We will finish up next time by looking at what happens in the average case analysis. I will stick around for questions, and we have office hours now for the next hour. Thanks everyone for coming.